Good evening, everybody, and thank you so much for joining us tonight. My name is Antoinette Handley, and I have the distinct honor of serving as the Vice Dean Graduate in the Faculty of Arts and Science here at the University of Toronto. Before I begin, I would like to start by acknowledging the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit. Today still, this meeting place is home to many Indigenous peoples from across Turtle Island. And with this land acknowledgement, we express our gratitude for having the opportunity to work on this land. Welcome to the 2024 Martin Lecture in Astronomy and Astrophysics. And a very warm welcome to you, Dr. Maria Zuber, the first woman to lead a science department at the storied Massachusetts Institute of Technology, and the first also to lead a NASA planetary mission. I'm so looking forward to Maria's presentation tonight as she explores the possibility of a human expedition to Mars. The Faculty of Arts and Science created this wonderfully, as you can see, popular lecture series to recognize the tremendous generosity of the Martin family. We believe it's a fitting tribute to the Martin family, known for their exceptional curiosity and their deep love of learning. Mary and Ron Martin's children are no strangers to the University of Toronto. All four, we have 3 of them with us today, earned degrees here at the University of Toronto. And so we welcome all members of the Martin family, however you are joining us tonight, in person, or I don't know if there are any online. And it's not just the children of Mary and Ron. The extended Martin family tree includes about 60, that's 60 family members, who are U of T graduates. Many of them multiple degree holders and dating back as far as the late 1800s. Clearly, this is a family that values education and learning, and one with a tremendous connection to our university. The Mary and Ronald Martin Graduate Scholarship, for which we are deeply grateful, these scholarships are a further and wonderful living tribute to this family's legacy. The Mary and Ronald Martin Graduate Scholarships are awarded to top students in 4 disciplines: astronomy and astrophysics, ecology and evolutionary biology, physics, and public policy, which are respectively the professional specialties of Mary and Ronald's children. And in the same way, the annual Martin Lecture Series, rotates also in focus amongst these 4 departments. So tonight's lecture is, of course, co-hosted by the David A. Dunlap Department of Astronomy and Astrophysics. The Dunlap Department is driving a wide range of outstanding observational and theoretical research, teaching and graduating the leading astronomers and astrophysicists of tomorrow. The department attracts graduate students from around the world who are eager to work with our world-class researchers and to actively engage in our prominent outreach programs. The past few months, of course, have been an exceptionally exciting time for those interested in astronomy, as eclipse enthusiasts across Ontario, Quebec, and the East Coast, we all looked to the sky in great expectation. We're going to hear more about humankind's fascination with the cosmos in the talk this evening. And to that end, I want to turn it over to Professor Roberto Abraham. Bob is a Fellow of the Royal Society of Canada. He is a former president of the Canadian Astronomical Society and, of course, chair of the David A. Dunlap Department of Astronomy and Astrophysics. Over to you, Bob.
So thank you, Antoinette. If I were a novelist rather than an astrophysicist, and I wrote a character with the biography of Maria Zuber, I am 100% certain I would be hauled up by some editor and told to cut 2/3 of what you're about to hear out because it's ridiculously unrealistic that any life form could have a biography this impressive. So it is such a thrill to welcome Maria Zuber here. She's the E.A. Griswold Professor of Geophysics and MIT's Presidential Advisor for Science and Technology Policy. She served for a decade as MIT's Vice President for Research. She was, as Antoinette mentioned, the first woman to lead a science department at MIT and the first to lead a NASA planetary mission. In 2002, Discover magazine named her one of the 50 most important women in science, and in 2008, she was named to the U.S. News Harvard Kennedy School list of America's best leaders. Over the course of her career, Professor Zuber has served 4 U.S. presidents. In the last decade, she played an increasingly influential role in shaping national science policy in the U.S., in particular as a member of the National Science Board, including 2 years as chair, and since 2021 in her White House role as co-chair of the President's Council of Advisors on Science and Technology. Now, today, she's here to tell us about Mars. This is a subject in which she's an internationally recognized expert, as her own research bridges planetary geophysics and the technology of space-based laser and radio systems. Since 1990, she has held leadership roles associated with scientific experiments or instrumentation on 10 NASA missions, most notably serving as the principal investigator of the Grail mission. She currently leads the gravity investigation on the NASA Psyche mission and serves as the chair of the Standing Review Board of the Mars Sample Return mission. How cool is that? Please join me in giving a warm welcome to Professor Maria Zuber as we enjoy her talk entitled, A Human Expedition to Mars.
Thank you, Bob. Thank you, Antoinette. And thank you to the Martin family. If you want to donate money to a university, there is nothing better than a lecture series that can reach out to so many people. So I really appreciate the opportunity to be here. So someday we're going to send people to Mars, okay? And I thought what I would do tonight is kind of talk about what that entails and what we know and what we don't know and kind of what we need to know to get us there. So let's start out here. So why on Earth would we want to send people to Mars? Okay, well, it's there for one reason, okay? And actually over the course of human history, societies that stop exploring stop advancing. Okay, so part of what we do should be the hardest things to do. There's a lot of hard things to do that are worth doing, and exploring space is one of them. And Mars has always had a fascination. Another reason is just self-preservation. That there should be a second planet with humans on, in case things went terribly wrong on the Earth. And I'm actually an optimist, but Plan B is always a good idea, even if you're an optimist. So let's talk about what we know and what we need to know. Okay. Today on Mars, okay, a cold, dry desert without much air, okay? People think Mars would be a wonderful place to visit. It would be. We'll see what you think at the end of this lecture. But today, it's a desert. Make no mistake about it. All right, so we've got to start with telling you a little bit about Mars, and I like to do this in the way of using fun facts. So this is the part of the lecture that you should listen really carefully, because if you remember some of this stuff, you will be great at cocktail parties, okay? Okay, so this is Earth and Mars approximately to scale, okay? Earth is about twice as big as Mars. Mars is just about the size of the Earth's core, okay? The surface area of Mars is approximately the same surface area as the Earth's continents. So Earth and Mars have about the same land area on the two planets, okay? The solar flux, Mars's flux that it gets from the sun, the incoming solar radiation, is 44% of what it is on Earth. So a bright sunny day on Mars is not as bright and sunny as a bright sunny day on Earth, even when the atmosphere is clear, and the atmosphere is often dusty, and we'll talk a lot about dust, okay? This is important because if we gotta go to Mars, we need power, okay? And if you think we can do it just by solar cells, not gonna be that easy, okay? Surface gravity on Mars is about 40% of what it is on Earth. And here's an amazing coincidence. On Earth, a day is 24 hours. On Mars, a day is 24 hours and 37 minutes. Amazing coincidence, okay? Earth's day used to be 6 hours, okay? But the lunar tide is de-spinning the Earth, and Earth's getting slower. So it'll be equal to Mars at some point, and then it will be longer than Mars. And 24 hours and 37 minutes sounds a lot like 24 hours, okay? Unless you're living on Mars time, unless you're a human who's living on Mars time. So the people who actually, virtually drive the Mars rovers around have to live on Mars time. And there are even watches with 24-hour, 37-minute clocks. You've got the worst jet lag that you can imagine after short periods of time, because humans are not adapted to a 24-hour, 37-minute day. Okay, here's another amazing coincidence. Okay, obliquity is a big word, but what it means is the tilt of a planet's spin axis, okay? So on Earth, it's 23.5 degrees. On Mars, it's 25.2 degrees. The tilt of the spin axis on both Earth and Mars changes drastically, okay, due to Milankovitch cycles. And so it's a coincidence that they're very similar. On Earth, we know that the tilt of the spin axis produces seasons. So Mars, in fact, has seasons, okay? And in fact, Mars's orbit is more elliptical than the Earth's orbit around the sun. So Mars's seasons are actually more intensely different than each other than the Earth's are. And then finally, here's a place where Earth and Mars are quite different. Earth has a nitrogen-oxygen atmosphere, and Mars has a carbon dioxide atmosphere. Actually, the only planetary body in our solar system that also has a nitrogen-rich atmosphere is Saturn, Moon's Titan. Okay. Venus has a CO2 atmosphere. Okay, more about the surface of Mars. Okay, so we talked about the CO2. The average, people say, Mars has an atmosphere. It's like Earth. So on Mars, the average surface pressure is 1/200th of Earth. So that's the equivalent of the altitude that spy planes fly above the Earth. Okay, so Mars at the surface doesn't have much of an atmosphere. And the surface pressure, it's a CO2 atmosphere, and it snows dry ice, okay? CO2... I think we don't have a mic now, so we're going to have to do something. I always say, if it's on Earth, we can fix it, okay? So. Okay.
Oh yeah, that's
Let's do that.
Thing saves the day, as usual.
Test.
Okay, all right, great. Okay, so the surface pressure the average surface pressure on Mars varies by over 30% over the course of a year, okay? Now, if you were at the center of a strong tornado or a strong hurricane, the pressure drop would be maybe 10%, okay? So think about a 30% difference in air pressure over the course of a year. The snow on Mars, as I said, it snows dry ice. Whenever the sun sets on the sun isn't shining on the atmosphere, CO2 begins to condense out, and it falls almost linearly with latitude, and it's about a meter deep at the North Pole and about 80 centimeters deep at the South Pole. And we measured actually the snow depth on Mars from a satellite before we measured snow depth on Earth from a satellite. So, fun fact. And actually, that was one of the measurements of our team. And we thought this was going to be a really easy signal because on Earth, you know, you've got 10 centimeters of snow, or 10 centimeters, 10 centimeters of water that nucleates corresponds to like a meter of snow. And so we thought, well, if it's a meter, that's going to be a 10-meter signal. It's really icy. It comes out of the atmosphere and it's really icy. So it's almost like ice, a little bit of fairy castle structure, but would be really bad for skiing, okay? Okay. Let's see, annual average temperature is minus 50 C. The temperature range, I mean, gets up to 21 degrees in the summer. So if you could stand on the surface of Mars without a spacesuit, which you can't, your feet in the summer, right on the equator, it would be warm, but your head would freeze, okay? Because the atmosphere is so thin that the heat falls off really rapidly. And then liquid water is not stable on the surface today. If you had a thermos full of water and you opened it on the surface of Mars and you poured it out, it would go right to the solid state by the time it hit the ground, okay? And abundant dust, lots and lots of dust. Okay, Earth is in this picture. Who sees Earth? Okay, yeah, okay, there it is, okay. So that is a picture taken from Gale Crater by the Mars Curiosity rover, and at the time that this image was taken, Earth was 160 million kilometers away from Mars, and actually, if you blow it up a little bit farther, you can see the moon as well. Okay, so so actually, we're very good at doing precise things on Mars. We know where we're at. Here's we got better cameras in orbit than we have at the surface, and here's a picture of the Earth-Moon system that was taken by the Mars Reconnaissance Orbiter, which is still orbiting Mars today. And I actually keep this picture on my the wall of my office because students come to see me and it's like, I want to go to Mars. What do I do? And I say, you want to go to Mars? Okay, everything you know and love is on that, okay? And it's 160 million kilometers away. Do you really want to go to Mars? Yes, okay? So, so there's plenty of interest in that. And actually, so what we do is there's lots and lots of things that you need to know to go to Mars. So you just start checking them off, you know, and you just do them. And then someday you're going to know what you need to do to go to Mars. And we're getting there. Okay, so if we go to Mars, we need hardware. So going to Mars, you need science, you need engineering, you need the social sciences, you need everything to do it properly. Okay, what do we have? We have a large launch vehicle. That one is a NASA vehicle. Later I'll show you a picture a SpaceX vehicle that would also be capable of going. This was tested for the first time successfully, but uncrewed in 2022. On the right side there is a crew vehicle, which 2025 or so, this rocket will take astronauts to go do a Apollo 8 like flyby back to the moon to get us going. Okay, so those are things that exist. There are other commercial crew vehicles that can now take us to at least low Earth orbit, okay, not to Mars, low Earth orbit. SpaceX Dragon, which has flown successfully for a couple of years now, and then maybe tonight the Boeing Starliner will launch. Okay, so fingers crossed. Okay, so on Mars, if we go there, we need a place to stay. We need surface transportation, and then we've got to get home. Okay, and so we've never launched a rocket off the surface of Mars. We've sent plenty of things to Mars. We haven't launched a rocket from Mars. Okay. All right, so let's talk about getting to Mars. Okay. All right, so here's the history of Mars exploration. Okay, so we got a couple things going on here. Things up there that are bright are successes, and things there that failed are grayish colors. And the turquoise colors are US missions, and the oranges and brownish types, those are Soviet Union or Russia. And then the yellows and greens are kind of everybody else. Okay, so the first thing that you see is that there's more failures early on in the system and more successes later in the system. You will also see that orbiters have a much higher success rate than landers, because it's really hard to land on Mars mainly because the atmosphere is dynamic. The wind is blowing and there are rocks on the surface. Okay, so what does the scorecard look like? Okay, so all the early failures on Mars led to the idea that there was a bad guy out there who was eating Mars spacecraft called the Great Galactic Ghoul. Never been seen, but who's actually doing better than we are in terms of missions that have gone to Mars so far, although we're getting better. But it's not really a fair comparison straight up, because when you look at the success rate in going to Mars, you should really compare it to something that's hard. Okay, so here's the comparison. Hitting a major league curveball is hard, okay? And the success rate of sending missions to Mars is better than the best lifetime and single season batting average that we have in Major League Baseball. So I'm holding out for when we're better than successful penalty kick percentages in soccer. Then we'll know we know what we're doing. Okay, so when we send an experiment to Mars, we need to communicate, and Earth and Mars are both in orbit around the sun. Mars is 1.5 times farther away. Sometimes Earth and Mars are lined up, and that's at the bottom, opposition, okay? And when that happens, it takes communications 8 minutes to get between the two planets. But Mars could be on the other side of the sun from Earth, and that's called solar conjunction. And when Mars is at conjunction, it takes 24 minutes. And actually, when Mars is right at conjunction on the other side of the sun, you actually get a blackout in the communications because of all the radio noise. Okay. Now, that is that's kind of stylistic. If we could add a little bit more information there, and so the orbit of Earth around the sun is blue, and here the orbit of Mars around the sun is red. And what you can see is that at oppositions, when Earth and Mars are the closest together, they're at different distances, okay? So, in 2031, we have a particularly bad distance between the two, which actually requires more energy to get there and more time to communicate. And then once we get out to 2033, it starts to get very favorable again. So there's all these things that you have to take into account when you're planning the mission. So then getting from Earth to Mars. So while you launch to go towards Mars, and both Earth and Mars are moving around the sun in their orbits, okay? So you kind of there are two classes of missions. The first is called a short stay, where you launch from Earth in brown, and then you arrive at Mars and you stay, this is called a short stay, 30 to 60 days, and then you launch back to Earth, but to get back to Earth, you actually come in, fly by Venus to adjust your orbit. You need to go inside the orbit of Venus to come around and get back to Earth. And the total mission duration is between 560 and 850 days. Or you could say, well, as long as we're going, why don't we stay for a while? And you launch from Earth, get to Mars, stay 500 days, okay? And so one Earth year is 365 days, one Mars year is 687 days, so it's nearly 2 Earth years. And then you can do a straight shot home in 6 months, but you're gone about 1,000 days, okay? So this turns out to be pretty challenging because of the issue of radiation, okay? So radiation is a big deal. There's 2 kinds of radiation that pose a risk to humans on Mars. There's radiation that comes from galactic cosmic rays, and that's coming in all the time, okay, at a sort of a low level. And then there are solar energetic particles, okay, where you can get a proton event, or you could get a solar storm that provides a short-term increase in the flux. And we care a lot about radiation because radiation affects humans. And so we have measured radiation on Mars. And radiation on the surface of Mars is a bigger problem than it is on Earth for 2 reasons. Mars doesn't have a magnetic field like the Earth does, or an active magnetic field, dynamo. And Earth's magnetic field keeps particles away from Earth, and then also the thinness of the atmosphere lets more particles through. So we have data from what radiation flux is on the surface of Mars. Also from orbit, we've measured Mars. You can see down at the bottom of that axis, the low level is mainly the galactic cosmic rays that are coming in. And then you see some shorter term events. And so if you see these short term events coming off the sun, you can actually run into shielding, okay? And that would be very helpful to you, whether you're in space or on the surface of Mars. Okay, another thing that you have to take into account is we have a solar cycle, okay? So the sun goes through a cycle over 11.2 years, and over there in 2020, 2019, the sun is not very active, and you get out to the front here, 2014, 2015, and the sun is a lot more active, and you get more solar particles coming out when the sun is active. And here, we've many, many years of observations of this, and so that's sunspot numbers, and those are solar storms, but that kind of generally correlates with the solar particles that are coming off the sun. So what does all this mean? So a dose, we measure radiation in a unit called sieverts, and if you had a dose of 1,000 millisieverts or a sievert, that's an increased cancer risk of 5%. And and then NASA has set a 3% career limit for astronauts who go to the space station, but they haven't set a limit for deep space missions. And so you can see measurements on there. For an 80-day transit to Mars, the radiation flux is about the same as spending 500 days on Mars. So, so the math doesn't work out here, radiation-wise, okay? And so shielding is going to be a big deal. So you can shield with, I don't know, say an inch of aluminum is one way to shield. You could shield with, on Mars, you could shield with dirt. You know, there are various ways you could shield, but shielding has to be a big part of the future. Okay, so then we need to get onto the surface of Mars. And actually, again, from the picture we took of Earth, you can see we know how to do things pretty precisely of Mars. So this is a picture taken from the same camera that took the picture of Earth and Mars that I showed you, of the Mars Science Laboratory that carried the Curiosity rover. So it's coming down to the surface of Mars. And so they were able to capture that from orbit. So we knew exactly where that was coming in. And so our rover landed missions lately in the United States have been very successful, okay? And other countries have not been so successful. Let's just leave it at that, because it's very hard. But coming down, there are rocks on the surface of Mars. So here's the Perseverance rover in an area that's kind of not too rocky, but the engineers actually want to know deterministically where every rock is so they could land safely. And when the United States rovers are coming down to the surface, the wind is blowing, you know, they're on a parachute, and there's a lot of dynamicism. You can't just target and go in. And so they've got cameras taking pictures many times a second as the descent happens, and then thrusters on the side. So if they're getting to a rocky area, they can move, okay? Because the same landing site, okay? Look at all the rocks in that part of the landing site, okay? This is the Perseverance rover landed at inside Jezero Crater, which used to be filled with water, and that's a delta that carried sediment and rocks from outside on Mars. And so, so I just want to compare this to these landings that have been happening at the moon. Okay, you have the intuitive machines landed, tipped over. Okay, the Japanese JAXA landed on the moon, tipped over. Okay. These landers do not have that capability. And there's lots of rocks on the moon too. So unless they get a more sophisticated landing systems, these landers are going to keep tipping over, okay? And so that's a capability that we have that will be important to humans too. Okay, we don't have the right kind of spacesuit. Okay, so actually on the Perseverance lander, that has taken with it samples of what could be the spacesuit that we have on Mars. So the visor, the polycarbonate, that's been taken, and these fabrics there, they are, you know, they're mainly, you know, like Gore-Tex, which keep water in, but are very slightly breathable, and they look at they're looking at the radiation degradation of these fabrics, and also that Vectran is on the gloves. So in the gloves, the astronauts need their hands to have mobility. So that that is being tested for the gloves, and important information is being collected on that. And here, that's a complicated chart made by one of my former postdocs. So I'm not going to talk about that chart, but just talk to you about the fact that humans are optimized for locomotion at 1G. Okay, so on lower G, it may be more energy efficient to kind of bound rather than walk. And you can build that into the spacecraft design or the spacesuit design in order to develop a covering that is going to allow you to go out and do the work on the surface of Mars in the most energy efficient way. Okay, all right. Now we're going to talk about dust. Okay, on the left-hand side there is the front of a dust storm, and there across the bottom, that's one of the Mars polar caps, and there is a dust storm coming off the polar caps, driven by katabatic winds that are coming off the caps, the same kind of winds that come off mountains, so they're due to pressure differences. And then on the top there is a profile, and the reflections there are dust particles in the Martian atmosphere, so we could see actually measure the density. Okay, on Mars, the mechanism, a primary mechanism of lofting dust in the atmosphere is dust devils. So over there, those are dust devil tracks at one of the landing sites, the Mars Exploration Rover. So that frightened us when we imaged that before the landing, as you could imagine. I think we have a little video of dust devils coming across the surface. Okay. So what happens here is here's a thermal infrared whole disk or whole hemisphere images of Mars starting June 17th and through August, so every day. And blue corresponds to a clear atmosphere, and red corresponds to a dusty atmosphere. So it turns out that dust storm season is summer in the southern hemisphere, because that's the point when Mars is closest to the sun. Okay, so the atmosphere heats up, dust gets lofted into the atmosphere. The atmosphere is very thin, so the dust heats the atmosphere a lot. And so the atmosphere that has the dust in it, the atmosphere expands, and it becomes less dense than the surroundings. And you wind up getting pressure differences, and pressure differences drive winds. Okay, and it can go global in a week. Okay, and it keeps. So here. Look at June 10th, July 31st. So you can enshroud the planet in dust. It's 1 micron sized dust, 1/1,000,000th of a meter sized dust. So it's very tiny dust, and it hangs in the atmosphere for weeks. And here's what the surface looks like during a dust storm. So you're not going to get a lot of power coming off your solar panels in dust like this. And so the way the dust storms end is the atmosphere finally gets so opaque that sunlight can't even get in. So you can't loft the dust anymore. It doesn't heat anymore, and it finally settles out. But it can take 6 months for the atmosphere to clear out. Okay, so obviously that's an issue. So you got to worry about where Earth and Mars are. You got to worry about where you are in the solar cycle, and you got to worry about when it's dust storm season. So you've got all these factors that you have to take into account when you're looking at the best time to go. So here's just some images from the Apollo program, and you can see how dirty the astronauts get with the dust on the moon. And they even, kludged to try to keep the dust from hitting them when they were driving around in their rovers. So because it's 1 micron dust, you've really got to have fantastic engineering in order so that dust doesn't get in and muck up the mechanisms. Okay, so a slight diversion. Okay, there is a phenomenon on Earth called zodiacal light, and it happens close to the equinoxes, which is the first day of spring, first day of fall, because the Earth passes through the plane of the solar system around then. And it's a brightening after dusk and before dawn, and it was thought to be caused by interplanetary dust that's in the plane of the solar system that was associated with asteroids and comets, coming off of asteroids and comets. And in fact, the guitarist on Queen, Brian May, is a PhD in astrophysics. He did his thesis on zodiacal light, okay? But there was a spacecraft going to Jupiter called Juno, and Juno on the way for fun and interest repurposed their star cameras to measure dust getting reflected off the solar panels on the way. And if you look over there, the highest concentration of dust is right around Mars. So actually the dust that we're seeing that's lighting up our sunsets and sunrises right around the equinoxes, that's Mars dust, okay? Not largely Mars dust. It could be some contribution from asteroids and comets, but it's predominantly from Mars, which is pretty exciting. Okay, all right, so now let's talk about what we have to take with us to Mars, okay? So, okay, think about we're exploring the western part of North America, and you start out with your mule train, and you got to take water, you got to take hay for the mules, you got to take oxygen. You're not going to get very far, okay? You've got to use, where you can, in situ resources. So what do you need? First of all, you need power, okay? Not going to be able to do it with solar panels alone. I think everybody here probably understands that perfectly at this point, okay? They say for a 2-crew mission, 10 kilowatts, it's not going to be a 2-person mission. It'll be more than that. We probably need 25 to 30 kilowatts in order to do a short duration mission. And so we're looking at nuclear power in order to power. So, I mean, it used to be when we put landers on the surface of Mars with solar panels, the rule of thumb was a kilogram, a watt, and a kilobit per second, okay? You got a watt of power, that's what you got. Now we've got more efficient solar panels, we can do a little better, but you go to Mars, you're power starved, no mistake about it. Okay, the good news is launch costs are decreasing, okay? So, so there's a picture of the SpaceX Starship, which has had a few launches now. They're getting more successful every time. Elon Musk wants to send this to Mars at some point, and he undoubtedly will. I don't really have a doubt. But let's look at how much it cost to launch something off the surface of Mars. And I just say to low Earth orbit, because most of the energy that you expend is energy to get you out of the Earth's gravity well. So the space shuttle, when it first launched in 1981, $85,000 a kilogram, okay? And then they got more efficient about things. In 1995, it was $26,000 a kilogram. Imagine that you got to take your HAB and your return launch vehicle and your water, etc. So we're now, the SpaceX Falcon 9 we're now down to $2,000 a kilogram, okay? Better, but SpaceX, Elon Musk says he's going to get Starship down to $40 a kilogram. That's what he says. And we'll see. But finally, we're getting decrease in launch costs. It was like $10,000 a kilogram for a long time. Okay, water. So water is heavy. So if you have water on Mars, you'd rather use the water on Mars rather than take water. So, so here's the present day surface water on Mars. So it snows CO2, but both polar caps of Mars are water ice, okay? And if you added up both water ice polar caps, the volume is 85% of the Greenland ice cap. So that's another, fun fact for you to keep in mind, okay? But there's more ice. Here's a map of water ice in the top 1 to 3 meters at the surface. And once you get above 30 degrees latitude, there's plenty of water ice that is accessible with a shovel. And it is there in sufficiently high weight percentages that it can't be in the crystal matrices of rocks. This is freestanding water ice. This is on the side of a ravine on Mars, and the blue is coded to water ice. So you can see there's lots of water close to the surface. And then finally, in the equator-facing sides of ravines and valleys, water actually melts and is liberated. So there's lots of water, and that's a good thing. So so water ice is something that you could have at Mars if you purify it, because it's salty. You need oxygen. So humans need to breathe oxygen, and you need oxygen for rocket fuel to get back. So there is an instrument on Mars right now. It's an MIT experiment called MOXIE, which actually produced oxygen. It used electrolysis to take carbon dioxide and break it into carbon monoxide and oxygen, and it's a 1 to 200 scale model of an in-situ resource utilization experiment that you could one day send to Mars too. So it's been demonstrated that you could, that we can make our own propellant out of CO2 on the Martian atmosphere. Okay, and then this is an eye chart, but this is just to say that for many areas of Mars, scientists and engineers have gone in, and you can make an assessment of how much sunlight you're going to get, how rocky it is, how much water ice there is below the surface that's accessible, et cetera, et cetera, et cetera. And you can characterize all these landing sites in great detail. And this is in drastic contrast to what we knew about the moon when we went to the moon. So when we sent the first landers on the moon, there were respectable scientists who thought that the lunar module would sink in foo-foo dust, okay? That's how little we knew about the moon when we went to know the moon. So we know a lot about Mars, and we're in a better place. Okay, so now I'm gonna play a video, okay? I'm almost done, but I'm gonna show you a little video of the Mars sample, the plan for the Mars sample return mission. Now, it's over budget, so it's being retooled. But this mission is to bring back rocks from Mars, and the idea is that it's going to do, for the first time, all the things that you would need to do to send an expedition from Mars. So you're going to land on Mars, collect stuff, put them in a rocket, launch a rocket off the surface of Mars, and then eject the sample part of it back to Earth. So if we could you play the video? Okay, so the Perseverance rover that's there now is picking up samples and putting them in little test tubes to be sent back. So you can actually watch the next lander come in, drive over to it. take the little rock-filled test tubes out of it, put them in a soccer ball type of enclosure, close it up. Okay, then this is a little ICBM-like thing. So first, launch off the surface of Mars, which we will observe. Okay, gets to Mars orbit. Rendezvous with a satellite from the European Space Agency that will be in orbit there. Put it in a hermetically sealed container. Okay, and then send it back to Earth, or maybe send it to Mars orbit, because we're going to have a space station in Mars orbit by then. So you could see there's a lot of things going on there in terms of that we haven't done before in terms of functions and what could possibly go wrong. Okay. All right. So let's just finish up here. Okay. All right. So this is my last chart, and I always like to end talks about Mars with a sunset. Actually, talks about any planet with a sunset. So on Earth, we've got Rayleigh scattering in the atmosphere that makes the sky blue, and then scattering close to the horizon that favors the red, so we get blue skies and red sunsets. And on Mars, because there's so much dust in the atmosphere, red light and yellow light scatters on the atmosphere, so you get pink skies, and then the sunlight coming through the atmosphere traverses most effectively at blue wavelengths, so you get pink skies and blue sunsets when you go to Mars. And so, in summary, what I would just say here is that the science is really far along. I hope I've convinced you that the science is far along, that scientifically we don't maybe know everything, but we know a lot and enough to go to Mars. And the engineering is hard, but it's doable. So when the day comes, when there is the will to send humans to Mars, we've got a good start. And someone, I believe, someone who is born right now, like you folks there, might be able to see a sunset like this in person. So I'll stop there and be happy to take questions.
Hello, test? Okay, great. Okay, let's thank Maria again for a fabulous talk. And so we'll have the next 20 minutes for a Q&A session. And so everyone, not everyone, but hopefully some of you will have a chance to ask some questions. So how we're going to work is we're going to have the microphone going around for people to ask questions. I also want to say the people who are online can also ask questions by typing the question in the chat, and our moderator, Jenny, will pick up a few questions and then read them out and let Maria to answer. And another thing is this whole session is being recorded and live streamed. So when you ask a question, your voice will be recorded, but not your face. So I hope that not keeping you nervous and encourage you to ask more questions. Yeah, and
Ask away.
And just to start, I want to say one thing I learned from this talk is if I'm not a scientist, so I'm an assistant professor at the Department of Astronomy here, and if I'm not an astronomer, probably I will make a ski resort and make those 1 meter dry ice ski resort to tell people, come experience here that you will see how you feel like if you're skiing in Mars. I think that's probably a good idea. Someone might pick it up and try it. Okay, I'll start that and then hope people have questions.
When we published that paper, I did so many interviews in Scandinavia and Canada.
Oh,
and-
that's maybe a business for Canadian to make such a kind of business. Yeah. Okay, we'll start. We have already hands up there.
So why don't we send people to Mars one way? I'd be willing to go.
You know what? You are not alone. There are plenty of people who have volunteered to go one way, and NASA wouldn't do that. The European Space Agency wouldn't do that. But there will be commercial entities that do that. Okay.
I'll join them.
Okay. So.
Okay, let's pick a question here.
Hi, if we're going to have humans permanently settled on Mars, how do we accommodate the difference in gravity and the effects on the human body?
Oh yeah, that's a very good question. So the astronauts who are on the space station need to exercise several hours a day to maintain their bone mass, okay, and their heart function, and so, but if you go to Mars and you stay for a while, humans are not adapted to stay long-term on Mars. So you either come back and, there's going to be adaptation in getting used to operating in 1G. I'm not envisioning a permanent settlement on Mars for a long time. I think about Mars and the moon the way I think about Antarctica. You go there. You've got a variety of people who go do field work. They come home. A couple of people winter over, so to speak, and then those crews get changed out. But if humans do decide to settle Mars long term, the human body is going to change to adapt to Mars. So that's a given. Human function will change.
Do you have any question online? Or?
Oh, the earliest date that people could land on Mars. So if we decided today to go to Mars, 10 years. Okay. SLS will be capable enough to launch, and the Starship will be capable. Now, you're going to need a Apollo program on steroids to do all the things that you need to do, but a decade from when a serious commitment is made to do that. But it's a matter of having the resources available to devote to it.
Great. We have one here.
Yeah. In your talk, you mentioned the need for oxygen and water, the dangers from radiation. You didn't talk about the dangers of mission failures and things like we saw with the space shuttle, and the contractors are really the same kinds of contractors. We still have Boeing working on this SLS and things like that. I wonder, also with how you showed how the sample return mission is going to happen, I just wonder, what's the motivation for people versus more advanced robotics?
Yeah, so that's, people can do things that robots can't, okay? But if you were there to kind of explore the geology, robots would win every time, okay? Where you would go to Mars is because humans want to have a presence on another planet. So you couldn't motivate right now sending humans to Mars simply because you could do better geology, okay? If you wanted to set up a mining operation on Mars, okay, if it turned out that Mars had certain kinds of heavy metals that we have a hard time finding on the Earth, that would require a human presence to be there. But that's a long time in the future. The reason to send humans to Mars is so humans go do something hard and explore in a far place. Okay, don't make the mistake of saying, you know, things will be better or more effective if we send humans, because robots can actually do pretty well. So.
Cool. We have a question on the back, I think.
Hi, how worthy and practically doable for us to grow food on Mars so we don't need to bring our own food?
See, I didn't.
Like whether we can grow food on Mars, like
Oh,
the potatoes.
How could we grow food? Yeah.
So we don't
that-
need to bring our own food. So we don't need to bring our own food.
Oh, well, you could grow food on Mars. I mean, there is dirt that's like Mars dirt. Okay, actually, the dirt that's most like Mars dirt is actually when you're going up the side of Mauna Kea. There's some dirt there that's really Mars-like dirt. But you know, scientists make Mars-like dirt, and you can grow stuff in them. So yes, it would be. I mean, not outside, but you'd need an enclosure and a greenhouse to do that. But there's nothing holding us back from growing food on Mars.
So basically, everything on Martian, the movie, actually can happen now if we can send people there.
That could happen now. There's no impediment to that. Yeah.
Great. A question here? Okay.
Does sending a human crew or colony to Mars imply a likelihood of organisms from the Earth spreading there, extremophiles, for instance? And can you comment on the implications of that?
Of us contaminating Mars? Okay. We've contaminated Mars. Okay. Already. So the United States has sterilized Mars landers, but lots of things have crashed into Mars that haven't been sterilized. So we have contaminated Mars, and Mars has contaminated us because we have many rocks in our meteorite collection that have been blasted off the surface of Mars, and there have been analyses of these rocks that show that in the process of getting blasted off of Mars from an impact of asteroids on the surface and flying through space and then coming through the Earth's atmosphere and then crashing, that the centers of those meteorites have not gotten to sterilization temperatures. So we actually worry a lot about contamination, and that's why those rocks were so sealed that we're bringing back. I mean, there's going to be a BSL-4 level like facility to handle those rocks when they come back. But we've, if we were going to die from Martian microbes, we probably would have already done that. So, but that said, care will be taken. Absolute care will be taken. So.
That's interesting. I just want to make a comment. Sometimes I go to like Mauna Kea or I go to Chile. I sometimes bring a rock back. I actually don't know if it's legal or not. Now I'm thinking about this. I don't know. I pretend I don't say that, but I just want to make a comment on that. I brought rocks from another country. I don't know if that's allowed actually.
Let's talk about real estate. On the moon, a lot of people are going after the South Pole because that's where the water is. You talked about the poles having water on Mars as well.
Yeah.
And related to that is the whole idea of lava tubes and getting there versus constructing your own little habitat and the cost-benefit analysis of all that stuff. So if you were a real estate developer, where would you pick on Mars? Would you pick the poles? Would you pick and would you do a lava tube or what?
Oh, lava tubes are really good for if there's a solar storm, right? That you've got 12 minutes or so and maybe longer, but 12 minutes from the time you get this solar storm and to know that you've got to take shelter. So there is time, but you could. So lava tubes are great, and actually there are lava tubes on Mars that are really long. Okay, so that's very convenient, but they tend to be in the volcanic regions that don't have as much subsurface water. So to me, the resources are the most important. So if you go all the way up to the poles, abundant water ice, but you don't get a lot of sunlight up there. So the sweet spot is in the mid-latitudes, in either where you have, water ice within a meter or two of the surface, and you have some sunlight. Yeah, and the water. You could, you could dig your own habitat. A lava tube is very convenient, but you could build your own subsurface habitat. That actually wouldn't be hard because the Martian atmosphere is very thin, and a lot of parts of Mars are very broken up. The impacts break it up. It's like a regolith, and it's you're not digging through just solid rock. It's pretty fractured, so it's diggable. So I'd go for the water and the sunlight. And
Okay, we'll take a lot of questions from the audience. Let's maybe pick one from online. Jenny, have one?
So one question is, can we build a lab on Mars that analyzes data and transmits to Earth in real time?
Well, we transmit from real time from Mars right now, so we could send a lab to do that, but we usually from the surface of Mars transmit to Mars orbit and then to Earth because we can get better data rates. But because we're so power constrained on the surface, you don't get large data rates from the surface. But it is possible to do a direct surface of Mars to Earth link. Yeah.
But it takes at least like 3-4 minutes.
It takes a while.
Yeah.
Yeah, and not great data rates, but it is done. Yeah.
Okay.
Okay.
Yes, we have my phone there.
You touched on it, and it's also been in the press about how the sample return is being delayed because of the costs. Is there a particular aspect of it that's being like such a big hill to climb that's what's getting in the way? Like, is there one that stands out?
It's hard. So we're doing a lot of things that we've never done on Mars before. So one of the things that's being looked at to really drive the costs down is a smaller rocket to launch off the surface of Mars. So that will decrease both the landed mass of the lander and just make it simpler in terms of the design of the lander as well. So NASA's put out a request for input. They're not like full proposals to look at concepts and space agencies. Canada, you guys could respond to it, and industry responses. So we'll see what we get on it. But the key here is this has to work the first time. This can't be like the SpaceX Starship that the first time it tips over and the second time it goes this far and then the fifth time it works perfectly. We don't have 5 tries. We don't have 2 tries, right? So so the cost now is $11 billion, and but it's the risk profile is a real challenge. So landed mass and the mechanics of the rocket are the biggest things, and then the containment facility that assures that the samples are completely isolated from the environment. That's another significant cost driver. That thing is pretty complicated. So.
Okay, we have one here.
With your background in dealing with public policy and that kind of dealing with the government and White House and that sort of stuff, do you feel that these types of missions would be private-public joint, or do you feel like it would lean more one way or the other? And I guess the follow-up to that would be, Do you feel like the general public would be interested in if it was more one way or the other and the costs associated with that?
Yeah. So I think the public would prefer lower cost, okay, for sure. I love partnerships, okay, and my view is anything that industry can do, industry should do, okay? That anything that industry is capable of doing ought to get contracted out and done, and the government should only be there for things that industry can't realistically do. And so already the current design for the rocket on the Mars Sample Return Mission is being done in industry, and so they'll get the opportunity for a redesign to see if they can shave some mass off it. It can be done, but there's going to be some cost associated with that. But it may, investing to save, that happens a lot. So.
Okay, for the sake of time, we will take probably two more questions.
We've got to take one here.
Okay.
Yeah.
We'll take two questions in the audience, maybe one from online. Oh, so we'll save that for the last one? Okay. Mm-hmm.
Hi, Doctor. My question is, you said that the science is almost there when we talk about going to Mars. So what's the blocker, and how can we get rid of the blocker? Do you see any any upcoming events that can help accelerate?
How do we get rid of the what? Blocker. The blocker. What's the blocker?
Like you said that the science and technology is already there.
Yeah.
And so what's stopping us from launching missions to Mars?
Okay. All right. Great question. So what's it's really expensive.
The money.
Really. I mean, if the cost of Mars sample return to bring 40 test tubes back to Earth is $11 billion, scale that up, okay? Because if humans are involved, the risk tolerance is going to be a lot more stringent than it is to bring those samples back. So that's what the real challenge is. Yeah.
Sorry, just to follow up to that. So you said that the finance or the cost is the main thing, what's stopping us. So do you see any tipping point at when it will be feasible?
I don't see a cliff. Actually the plunging of the launch costs. I mean, if Starship comes down to $40 a kilogram, that will be a real enabler. Okay, there. But it's when humans are involved, just the amount of testing and how do you prove you've got a 98% probability? It's a very hard thing to show, and you're not going to be able to just do that on paper. There's the amount of testing that you're going to. So there's going to have to be multiple prototypes built. But it's doable. You can see when there's a big piece of science missing, then that's a real impediment. But this is mostly an engineering challenge now, more than a science issue. The radiation, we got to work that for sure. Okay. So.
Is there any question from online? We want to pick the last one there before we go to this one here. Yeah.
Oh, yeah, okay. So, I've been asked that before, okay. So we should spend a lot of money to deal with challenges on Earth. There's absolutely no question about that, and we do, okay. But I think I said this when I was talking to the graduate students this morning. If we didn't build the James Webb Space Telescope and we put that into an AIDS vaccine, we still don't have an AIDS vaccine, and we wouldn't have a James Webb Space Telescope. So we actually, you know, you need a broad portfolio of investments to do a lot to help people, but also to do really, really challenging and hard things to advance as a society. And so, and there's a lot of public support for that. So.
Okay, here.
Yeah.
Hi, thank you so much for coming. It's a wonderful lecture. I was wondering, do you see the possibility of a permanent colony on Mars at some point in the future? And if so, what would the biggest challenges be for that?
Yeah, so the challenge to a permanent colony on Mars, I think the biggest one is radiation, actually. You know, you can, there's water, you can figure out how to grow food. You know, Mars was made of the same, is made of the same elements that form the Earth. So the elements that are on the Earth are on Mars. So you could make stuff. You know, there's iron oxide all over Mars. So you could make steel if you wanted to make steel. But you know, it's far away, and you're going to use what you have. So it's you know, you've got to use what's there. So that's the real challenge. And again, human physiology will have to adapt over time because we're not adapted to living in that environment. So.
Okay, thank you. As the moderator, I hope I have a privilege to ask actual last question. Actually, I have two, but I probably pick one. So I'm not sure if Bob mentioned, but as Maria, you have been holding leadership for like 10 NASA missions, and also have mentioned that you have been leading the first woman, I've been the first woman to lead the NASA planetary mission. Can you, and we have a lot of students here, a lot of junior people here who probably are enthusiastic to dive themselves into space exploration. What will be the #1 advice you will give to them if they wanted to work on this Mars mission, like say 10 years from now or 5 years from now?
Yeah, study hard.
Study hard.
Study hard, you know. It's, there's no reason that you couldn't be involved in Mars exploration if you wanted to be involved in Mars exploration. But you gotta be, you gotta study, because there's a lot of competition, so.
And the two last questions, sorry. You mentioned in one of the slides that I think in 2033 or 2035, we're gonna get closest to Mars, about like 20.4 AU or even less. Do you think if that's the time we're actually gonna launch something and do the last movie that you showed, likely that's gonna happen in 10 years from now?
It could.
Okay, okay. So I guess the conclusion is people here need to work hard to make it happen in 10 years.
Elon Musk is gonna go, so. And
you're gonna buy this one-way ticket?
And he's not gonna ask permission, so.
Okay.
So.
Okay, great. I would like to thank Maria again for a great talk, a great lecture, and thank Martin family to support this. I want to say the talk reminds us, some of us who are scientists, engineers, to think about why we are here. We are doing this not because it's easy, because it's hard. And this all the challenges we heard, and we will overcome hopefully one day. And hopefully inspire many of you that the junior people that one day you will also choose that path. Okay, thanks Maria again.